So for this next video, the topic that we're going to be discussing is orbital hybridization, or in other words, how certain orbitals, specifically in the carbon atom, are going to be creating certain hybrids that we're going to be using to determine our bonding and everything else related to organic chemistry. So we have to remember carbon has atomic number 6, meaning that it has 6 electrons arranged in the 1s2, 2s2, 2p2 fashion. And if we draw this as a diagram of orbitals, we're going to get that there's, in the 1s orbital, we have 2 electrons. And then the 2s orbital, we're going to have 2 electrons. And then in the 2p orbital, X, Y, and Z, we're going to have only 2 electrons. Now, if you remember from other courses, our valence electrons are the ones that are on the highest shell. So in this case, shell number 2. And that gives carbon 4 valence electrons, making it a perfect candidate for covalent bonding. So if we look at the highest shell, which is precisely 2s and 2p, we only have 4 electrons that are going to want to form a variety of covalent bond formations, maybe 4 single bonds, or maybe 1 double bond and 2 single bonds, or maybe even 1 single bond and 3 and a triple bond. So in this case, this is where the theory of orbital hybrids comes in. Let's say that in an unhybridized form in its valence shell, well, carbon has 4 different orbitals, and these are represented by S, which we're going to code here in blue as a sphere. So this is the S in the valence shell. And then we're going to have P, which we're going to code in pink. And pink can be on the y-axis, on the x-axis, or on the z or z-axis, right? So these are unhybridized s orbital, py, px, pz. So in an unhybridized form, carbon is actually not forming a hybrid. We have 4 distinct orbitals. But now let's quickly make the same picture over here, and we're going to try to fashion out a little table where we're going to try to show you specifically how these hybrids could actually work if we start to combine them, right? So remember, each carbon atom is going to have exactly 4 orbitals in its outermost shell, in shell number 2. And these are in the unhybridized form, right? So let's say that we go ahead and we decide to mix all of these orbitals together. And the result of this recipe of S, P, Y, PX, or PZ is going to be, when we mix all of this, we're going to get a recipe called sp3, because it's made out of 1s and 3p orbitals, right? So if we plot that same quick drawing of the axes, we're going to head, and I'm going to code these in blue and green, I'm sorry. We're going to get 4 distinct orbital hybrids that are going to be pointing in different directions. And each of these green shapes that I drew is actually a different sp3 orbital, that if we put it together to form a single carbon atom, we can make a shape such as this. And I'm going to shade it in and then just draw a contour so that you can see exactly the shape that I'm allegedly drawing, and then one pointing to the back. And these orbitals want to be as far away from each other as possible. So the predicted shape of this new carbon atom, which is all hybridized, is a tetrahedron. So a pyramid with a triangular base, where the angle between each of the orbitals of separation is 109.5 degrees. So Curiously enough, sp3 is characteristic of single bonding molecules or alkanes. And it takes on this tetrahedral shape when carbon is only single bonding. Now, let's try another type of hybrid. Let's say we prepare this recipe where the only thing we're mixing is an S with two p orbitals, meaning that we have an unhybridized p orbital left over, and meaning that we're going to get 3 hybridized orbitals that, again, are going to be as furthest away from each other as possible. And then we're going to get this shape in which the sp2 orbitals are all as far away from each other as possible on a planar form. That means they're all lying on a plane. And here what we're doing is I'm drawing this unhybridized p orbital. And what we can see here is a shape that we're separating here of the hybrid orbitals. Imagine these are all on a plane. So the angle between these orbitals as they're separating from each other is 120 degrees. So a circle, looking at it from the top, exactly divided in 3 parts, each 120. So curiously enough, sp2 hybrids are characteristic of double bonding molecules, alkenes. And so this is the shape that they take, right? So the hybrid orbitals want to join together with other orbitals in another carbon atom. And once again, each of these flower or balloon diagrams is actually representing one carbon atom. And last but not least, if we do the last mixture is sp, which, as you may know, is characteristic of triple bonding molecules, also known as alkynes. And in this case, when we mix the hybrids, remember, we're only mixing the s orbital from the original unhybridized orbitals in the second shell of carbon in the outermost shell. 1s2 doesn't count right now. So 1s2 to s2, carbon with the atomic number 6. And when we mix the s with 1p, we're only going to get 2 hybrid orbitals as far away from each other as possible. And we're going to get left over 2 unhybridized p orbitals. This is a p orbital, this is p, this is p, this is sp, sp. And as you can notice, all of these different styles of carbon hybrids have 4 orbitals. It's just the difference between 4 hybrids, 3 hybrids and a 1 non-hybrid, or 2 hybrids and 2 non-hybrids, which basically can be represented like this. And then I tell my students these are kind of like rabbit ears popping out, which represents 2 of the p orbitals which are not hybrid. And then here we have the hybrid orbitals, 2 of each. And if we were to trace a line here and measure the bonding angle, we have a straight line 180 degrees, which is straight across. That means that one's pointing left and one's pointing to the right, exactly in a line. So now how does this all become relevant? Because let's say that we want to look at how this is actually structured. So for example, if we take this molecular formula, C2H4, this is the formula for ethene, and ethene is an alkene. So we're going to draw its expanded structural formula, double bonding C, and then we have hydrogen accompanying that carbon on each side. And since we know from this page that sp2 hybrids are characteristic of alkenes, we're going to draw this to represent each carbon. So this carbon, carbon number 1, carbon number 2, we're going to draw it. So first I'm drawing my hybrids with a non-hybrid, and I'm going to shade this again to show you guys exactly what I'm doing. And interestingly enough, in order to connect this, we're going to draw its mirror image. And its mirror image appears like this. I shade it in again. And once again, for those of you who are watching right now, we're drawing carbon atoms, right, in its sp2 hybrid form. So here we have an sp2 carbon with another sp2 carbon with 3 hybrids each and 1 non-hybridized item. What are we missing? Hydrogen. Hydrogen's configuration is 1s1, meaning that it only has an s orbital present. So we're going to represent that joining here at the edges as a little sphere, which I'm going to code in blue. And this is basically our complete molecule. Now, I'm going to draw another really quick molecule right here, which is ethyne. Ethyne is an alkyne, meaning it has a triple bond between the carbons and a single hydrogen in each side to complete carbon's 4 bonding pattern. Now, as I showed you in the last picture, I draw my 2 hybrids kind of like an infinity sign, straight across from each other. And then my rabbit ears. Then I'm going to draw the exact same shape to represent the other carbon, carbon number 2. And I shade my hybrids in green so that I don't lose my order and that I know what I'm looking at. And again, the pink is unhybridized p orbitals. And then we're missing the hydrogen here on the sides, which we're going to represent with blue spheres representing that unhybridized s orbital. And here we have 2 sp atoms. Now, if we remember the anatomy of each of the hybrids, each sp3 carbon has 4 orbitals, all of which are hybrids. Each sp2 carbon has 4 orbitals, 3 of which are hybrids, and 1 which is unhybridized. And last but not least, the sp carbon has 4 orbitals as well, but only 2 of them are hybrids, 1 and 2, and the other p orbitals, which are also 2, are unhybridized. Now, let's talk about another feature of this bonding that we're predicting with our orbital hybrids. And we're going to talk about sigma bonds, which I drew here, lowercase sigma. This is a letter between brackets and pi. So sigma bonds are, all single bonds are sigma bonds in any molecule, right? So this hydrogen-carbon bond is a sigma bond, this hydrogen-carbon bond is a sigma bond, and this hydrogen-carbon bond as well, also hydrogen-carbon, etc., right? So once we determine this, it's a way that we count to see how many bonds are actually occurring. From this expanded formula, we know that ethene has 1, 2, 3, 4, 5, 6 bonds, and these 2 bonds in the middle actually constitute one single conceptual bond, which is a double bond, right? So in other words, you could say that there's actually 5 bonds, a double bond and 4 hydrogens, or that there's 6 bonds because I'm going to explain right now the anatomy of a double bond. So let's go back to this. So as I said, hydrogen and carbon are making a sigma bond, and I'm going to use purple pen, no, red pen. I hope that it shows on the video. And this bond, which is this one right here, is this one right here. It's a sigma bond. Also this one, and also this one. But what's characteristic is that any double bond is made up of 2 things. The double bond is 1 sigma bond and 1 pi bond. So the sigma bond is occurring between the hybrids, and the pi bond is actually that inflexible bond which gives alkenes their specific cis and trans isomerism, which I will explain in another video. But when we connect this, and I'm showing you this with hatched lines, these 2 p orbitals are linking to each other. That's why they need the mirror image to form a pi bond. So if they were to ask you how many bonds do we have in total, we have 6 bonds, out of which 5 are sigma and 1 is a pi bond. So the double bond gives us 1 sigma bond and 1 pi bond. And if we follow that same analysis right here, we have 5 bonds in total for ethyne. And we know these two orbitals are joining in a sigma manner. This is a sigma as well. And these 2 hybrids are sigma. So there we have 3. But then we have 2 specific p orbitals on each of the atoms, which if we connect with these hatch lines, we have a total of 2 pi bonds. So 3 sigma and 2 pi bonds together. Why? Because a single triple bond is made up of 2 pi bonds with 1 sigma bond in the middle, connecting the hybrids. So once again, to have a recap of what we're analyzing here, remember the double bond is made of 1 sigma bond and 1 pi bond, and the triple bond is made up of 2 pi bonds and 1 sigma bond. So in other words, all single bonds found in a molecule are sigma, and also 1 bond in the double bond and the triple bond is sigma. And pi bonds are only found in double and triple bonds, where 1 single bond has 1 pi, and where a triple bond has 2 times pi, right? So let's analyze this in another fashion where we're, of course, gonna keep on thinking about hybrids. But let's say we have a molecule that's not super complex, but we're drawing a carbon backbone molecule right here, showing only the position of carbons. And we can use the general formula for alkynes, CXH2X minus 2. So in this case, we have 5 carbons, C5, H 2 times 5 minus 2, which is going to be equal to our molecular formula, C5H8. And now if we try to figure that out, how it works, this carbon is bonding once to the side, so it's missing 3 hydrogens. This carbon is establishing 4 bonds, 1, 2, 3, 4, so we're full. 1, 2, 3, 4, this one's full. And then this one is making 2 bonds, so it's missing 1, 2. And this final one is establishing 1 bond, so we're missing 3. What are we missing? Hydrogens. So the bonds that are actually present. And if we count the dots, 1, 2, 3, 6, 7, 8, we have 8 hydrogen atoms which are present in our molecule. Okay. Now, a quick mathematical way to do this is remember that the hydrogens are establishing a single bond with each of the carbons. And if we look at our previous page and we remember that each triple bond has 2 pi bonds and 1 sigma, there's a very simple way to calculate this, which would be that sigma bonds are equal to the amount of carbon minus 1 plus the amount of hydrogen, which we can get from our molecular formula, which we counted or we just devised or derived from our general formula for alkynes. So in this case, the amount of carbon is 5 minus 1 gives us 4. And the amount of hydrogen is 8. So in total, we have 12 sigma bonds. And the amount of pi bonds is equal to this formula. Double bonds times 1 plus triple bonds times 2. So in this case, we have no double bonds, so it's 0 times 1, 0 cancels out, plus 1 triple bond times 2, and the answer is 2. So the total number of bonds is 14, out of which sigma is 12, and pi is 2. Now let's see if that works out when we do the expanded formula. C, 1, 2, 3, 5. Then we connect this. Then we have in our expanded form, we're showing this. And now let's count. Okay. So sigma bonds, our target is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why are we missing 1? Remember, 1 of the bonds in the triple bond is sigma, so this is our 12th bond. And where are our pi bonds? 1 and 2. And that's how we prove what we're doing is correct. Let's try another example. We're going to draw another large molecule. Let's say C. And I'm just making this up, okay, you guys? It's nothing special. I'm just trying to show you that this works no matter how big the formula is. So let's try that method I showed you with the dots. And here we go. So this carbon is making one bond. So it's missing 3. 1, 2, 3. And then this carbon is making one bond, so it's missing 3. This one is full. 1, 2, 3, 4. 1, 2, 3. It's missing 1. 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 1. It's missing 3. 1. It's missing 3. Let's count our dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's my amount of hydrogen. And then carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. C9H16. And now, let's see if this works out. So, the formula I showed you for sigma bonds is carbon minus 1 plus hydrogen. So, that would be 9 minus 1, which is 8, plus 16. That means we have 24 sigma bonds. Pi bonds is equal to double bonds times 1 plus triple bonds times 2, which would be equal to, we have 2 double bonds. 2 times 1 is 2, plus 0 times 2 is 0, and my amount of pi bonds is how much? 2 pi bonds. So total bonds in general are 26. And now let's copy this formula down, and we're going to complete it with its hydrogens to see if what we're doing, we're double checking our work to see if it's correct. Okay, so now let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, yes, 17, 18, 19, 20, 21, 22, 23, and 24. So we're good. Sigma is equal to 24. And then remember that each double bond has 1 pi. So pi bonds is equal to 2. Total number of bonds is 26. And we did a good job. So I hope this tutorial on orbital hybrids and how things work out with the bonding was helpful. And leave any comments or questions down below. Thanks.